a little bit. Everyone got the homework up there? Homework 3 from the book. We'll call it homework 3, but those are the problems you're doing tonight. Yeah, get back. Oh, you're leaving. See ya. All right. So, So this is somewhat review from pre-calculus, but let's just say that by an infinite series, of course, we mean some series that goes on forever. You could write it in summation notation with an infinity up here, or with triple dot notation, so that it indicates that we've got an infinite series. And of course, a question of interest to us is, does this set of symbols even make sense? And of course, sometimes it does if it converges, and sometimes it doesn't if it diverges. So we'll entertain that question on the next slide. But let's just practice quickly your ability to write something in summation notation. Can you do it? Let's just remind ourselves how to write something in summation notation. It's been a little while. What do you mean?
Why was it only from x is greater than or equal to 1 rather than 0?
For which one? Well, I think one of them started at 1, didn't it? The second one?
The top one was from 0 to pi, and in the written proof, you said x is greater than or equal to 1.
I don't think so. I'll just for you.
But then, right below, you wrote for all x is greater than or equal to 1.
For all x greater than or equal to 0. I saw the 0 to pi and I was like, that looks cool. Good call. Anyone want to venture into this one? I used K up here. You want to use K? You can use I, J, something near the middle of the alphabet. Whatever you like, M, N. I try to give you like as interesting as possible one. Let's break it into a couple of questions. First of all, what's your favorite letter? Let's use, no. Has to be near the middle of the alphabet, sorry. K. We can use K. N is fine too, whatever, yeah. N equals. Now, let's reserve judgment on what we want to say here until I hear someone say one of these. Where do you want to start? Pick one and tell me what the rule is for it. One thing in this expression. There's a lot going on. Yeah, Shivani. Is just 5 to the k. So, all right, so by saying that, you've just said that we're starting at 1. Okay, all right. Everyone okay with her choice? She has bound us all to start with 1 now. All right, that's fine. Someone take another part of this expression and hit it, Ashley. K cubed. You guys agree for that first part? Down the bottom. Times, what'd you say? Oh, yeah, that's true. This is terrible, right?
1 plus k minus times.
It's something factorial. All the odd numbers, I guess. Yeah, 2k minus 1. You always have to kind of think, is it 2k minus 1, 2k plus 1? Oh, we're starting at 1. Okay, so 2k minus 1. Try that on for size. Is that working? Are we done?
No.
What else do we need?
Oh,
We need an infinity. Yeah. Are we good? Now we're done. No. What do you see, Laura? Where are you shaking your head? Oh. I don't know how to get that to happen. What do we do? Huh? Say it again. Yeah, I like that idea. -1 to the k. But if we do k, she's saying then we'll get negative, positive, negative, the opposite of what we want. So I don't know, there are a couple ways. You could throw a negative out front. Or you could do, would you say k plus 1? Sure. Or k minus 1. Whatever, the point is. That's all good. So anyway, I think this finally works. Whoa. All right, that's intense. I tried to throw like all sorts of stuff at you in one problem, didn't I? I have to think about odd numbers and factorials and cubics and geometric things and alternating signs. There it is. It's everything. I just wanted, rather than doing multiple examples, one example. It has it all. All right. I'll just remind you of these things. You can take a picture. Oh wait, no, sorry. That's the next slide. So by an infinite series converging, remember that we mean that the partial sums converge, right? So add up the first term, add up the first two terms, add up the first three terms. Are you getting something that's that sequence of partial sums? Does that seem like it's going somewhere? If so, that's what we mean by the series converging, right? So each one of these, just like what we did with integrals, right? It's like swap out the upper limit instead of infinity, because that might be ill-defined. Swap it out for another letter. And then ask, what is the limit of the sum going toward? So we can talk about series either converging or diverging in the same way that we've just been talking about with integrals. So by this symbol, we really, just at any moment, if someone questions you about why this makes sense, just be like, well, what we really mean is this, right? Just the limit of a partial sum as that upper limit grows. You know? And I promise at some point we'll make the connection back to integrals. We want to say both things. But already you're maybe already starting to see some connections, and especially on this next slide, you'll be like, oh, wow, that sounds familiar. But in some ways today just serves as like a review of things that you learned at pre-calculus, or, yeah, hopefully you learned. Summation of fictions. Infinite series. And on the next slide, the convergence test that you learned in pre-calc. Now, I don't know where all of you are coming from, but I think it's at least in IE pre-calc, honors pre-calc, but in all those, we teach these rules. They came up on the summer packet too. So, do you remember these? Like I said, you might want to take a picture if you like, or if you want to grab the slide online or whatever. I mean, these should all theoretically already be in like your notes from last year or something. But and we'll actually do a few more too. We'll do a few more too, but let's just highlight these and just nod and be like, oh yeah, I remember that. Well, actually, we'll start down here. The direct and limit comparison tests, friends, are the ones we just did. Now, the one thing that we have to regret and feel bad about last year in pre-calc is that we gave these to you and said, don't these kind of make sense? And you're like, uh-huh. But technically, you can't prove. It's difficult to prove in particular. Well, yeah. Well, yeah. I mean, these connect with the things we're doing here right now in terms of like why they work. So, you know, we'll have to come back to these with a proof maybe. But certainly they work the same. It turns out that they work the same way as the tests we've been doing in the warm-up today. For series though, right? We're just like, does the infinite series 1 over k squared converge? Yes, it does, right? You can use the same. It turns out you can use the same tests. And again, a proof is still forthcoming for that, but we're going to make a connection between those, and we'll prove all of these. So let's return to the top two because you haven't thought about them in a while, but I promise you did hit them in pre-calculus. So this makes sense, and I want to make sure you understand what it says and also what it doesn't say, and just remind you what it doesn't say. So if you have the terms of a series and those diverge, you have a series like, oh, I don't know, n over n plus 1. Terms themselves, forget the sum. The terms themselves are getting ever closer to 1 for that series. So what happens when you start adding them up? Well, of course, that's not going to go well. As a first test for a series, certainly the terms themselves that you're going to add up, if you're going to add up an infinite number of things, they better be getting closer and closer to 0 if you have any hope of it converging. Now, as you know, for a series like 1 over n, which diverges, it's not good enough to just have them be approaching 0. If the terms go to 0, does that imply convergence? No. In fact, that's why we usually call this not just the nth term test, but the nth term test for divergence, just because there's never a time that you'll ever say, by the nth term test, this converges. There's not a single series we'll ever say that about, right? But it does help us very quickly weed out divergent series. So this is ringing a bell, this discussion? Sophie, that's really geometric series test. Remember that geometric series converge or diverge, and that's going to be the focus a lot in the coming days here and today as well. Converge or diverge whether the common ratio is in absolute value less than 1. And furthermore, unlike a lot of these other series that aren't geometric, we can actually say what the sum is. And I assume that you encountered the proof of that in pre-calculus, right? And so we can run through that again, but we'll just assume everyone remembers that it's the first term over 1 minus r is what the sum is. Okay. So you took a picture, you thought about these, we've been reminded of these, and so really, like I said, today's purpose is just to review a little bit. Let's do a couple examples now. I'm just going to throw a bunch of series at you, and you tell me whether they converge or not, and why. And if so, if possible, find a sum as well. So let's start with this nice one. Simple, I don't know, probably example you first encountered in pre-calculus too. What do you think? Why? Give a reason. Huh? It doesn't, say it again? It doesn't approach 0 is a fine way to say it. Yeah, and the reason I ask why is because a lot of you could have there could be some different explanations on this. Terms don't approach 0. This series diverges. The other thing you might invoke is the definition of what we mean by an infinite series, right? The partial sums. What do the partial sums look like? 1, 0, if you're adding them up. 1, if you add up all those terms. 0, right? The actual partial sums are that if you add up the first 20 terms, does that get closer and closer to something? The first 21 terms, 22. Well, no. The partial sums actually aren't converging, right, themselves. Nice. Very basic example of what kind of series? Yeah, convergent, but what more precisely? Yeah, it's geometric with r equals what? So it converges, and we can say what the sum is also to 1 over 1 minus 1/2. So what does that come out to be? 2. Good. Yeah. By the way, the picture that I showed you on the opening slide of this unit on two days ago was a picture of that series which summed to 1. Do you remember that? 1/2. Starting with 1/2 plus 1/4. You saw a picture of that. That converges to 1. So it doesn't surprise us that 1 plus all that converges to 2. I told you this would all be kind of reviewed here. I'm going to give you a second to think about those two. We'll come back together. I just want to make sure that I hear from the people. What'd you say on this one? Here, I'm gonna, how about Cassia, give us your answer all the way out here. What kind of series is this? What'd you say? Cassia, yeah. Okay. Do you want to give the sum too? How'd you get that? Was it sum is 2 over, is 2 the first term? 1 minus 3/5. I think I'm with you on that. Yeah. Anyone take a look at this guy? This is a little tricky because on the other ones we've given a rule, so we actually have to venture into that land where we give a rule. So let's give a rule. It's not too bad on this one, not as bad as the first one we gave today. What is it? You want to use n's or something? Yeah, we definitely have like an n squared on top, and not sure how to handle this on the bottom. What do you want to say? 9 minus n. If n is 1 there, then I think that makes sense. Does that work? What do you think on this one? Why does it diverge? Later. Yeah, the terms themselves don't approach 0. We're just getting back in our mode here. It's been a while. Right? The actual terms approach infinity. Or actually negative infinity, but whatever. Okay. And actually there's another problem with this one too. At term number 9, there's a little bit of an issue too. So maybe it's just not even well defined. Oops. Okay. Can we do another one? Yes. I'll put these both on the board to see if you guys see. What kind of series is this first one? Anyone have it yet?